Well, hello, hello. Today I want to talk about the product rule, which is going to be another rule of differentiation that allows us to differentiate functions that are products of functions that we already know how to differentiate. Now, I want to recall some rules that we're already aware of for taking derivatives. If we have the derivative of a constant times a function, we can pull the constant out front and multiply that by the derivative of the function. We also have two rules that say if we have the derivative of a sum or a difference of functions, we can just take the sum or difference of the derivatives, meaning we can differentiate the individual functions and then add or subtract them. Now, one might be tempted to guess, as some famous mathematicians have in the past, before this rule was known, that it might be the same with products. Now, what I mean by that is that if we want the derivative of a product of functions, f of x times g of x, we don't know, we might hope, we don't know, but we might hope that that is equal to the derivative of the first function times the derivative of the second function. Wouldn't that be nice? If this were true, it would mean that if we were differentiating a product of functions, we could just differentiate the first and differentiate the second and then multiply whatever the result is. Now, based on the way that I'm speaking, saying wouldn't it be nice, you can probably guess that this is not how things work. And that is the case. I don't want to just tell you that it's not the case, though. I want to show you how we know that this doesn't work. Let's look at an actual example and see what happens. Let's consider f of x equals x to the fourth, and g of x also equals x to the fourth. Now, if we applied this fake rule, if we try to differentiate the product x to the fourth times x to the fourth by differentiating each one on its own, so that's d over dx of x to the fourth times d over dx of x to the fourth. Well, we know the derivative of x to the fourth is 4x cubed. So we would take 4x cubed times 4x cubed. And what does that give us? 16x to the sixth. However, we know that x to the fourth times x to the fourth is x to the eighth. So really what we're differentiating here is x to the eighth. And we know from the power rule that's going to be 8x to the seventh. Is that the same as what we got when we differentiated each of the factors individually? It's not. These two things are not equal. I know that it's weird to put a not equal sign between them like that, but these two things are not equal, which means that this method that we used is not correct for differentiating x to the eighth. So I'm actually going to write a cross through this equal sign. It is not equal to that product. If it was equal, if that was a way of differentiating a product of functions, then we would have ended up with the same answer. So this is not the case. And so the product rule has to be something different, if there is a rule at all. Now, the mathematician Leibniz eventually found the correct formula, and so I'm going to give that to you right now. Now, at first glance, this is going to look complicated, but that's just because there's a lot going on with notation. I promise you it's not that bad. You'll get used to it very quickly. The product rule says if f and g are both differentiable functions, and we want to take the derivative of their product, we can. And the way that we do that is we take the derivative of the first times the second function itself, plus the derivative of the second times the first function itself. And we can look at this in simpler notation. If we want the derivative of a product, it's the derivative of the first times the second, plus the derivative of the second times the first. It's really not that scary, I promise you. So what I want to do is I want to do a few examples. All right, first, to show you that this actually is true, let's look at this example that we had just looked at earlier. Let's try and differentiate x to the fourth times x to the fourth. Now, we know that x to the fourth times x to the fourth is x to the eighth, and we know that its derivative is 8x to the seventh, but let's pretend that we didn't know that, and let's go through and use the product rule and make sure that we get the same answer. So, when we use the product rule, it says that we've got to take the derivative of the first times the second. So the derivative of the first function is 4x cubed times that second function itself, which is x to the fourth, plus the derivative of the second function. Now, the derivative of x to the fourth is also 4x cubed times the first function. That first one is just x to the fourth. And if you look at both of these, we've got a product. 4x cubed times x to the fourth is 4x to the seventh. We add those exponents. Plus, the other term is also 4x cubed times x to the fourth, which is 4x to the seventh. And when we add those together, we get 8x to the seventh, which is exactly what we had when we differentiated 8x to the eighth directly. So this just shows us that we are getting an answer that is reasonable, unlike this other fake rule that we maybe tried to look at earlier. All right. Now, you would never use the product rule for this because you would just take x to the fourth times x to the fourth, write it as x to the eighth, and the derivative of x to the eighth is 8x to the seventh. This is not a situation where you'd really want to use the product rule, but we're using it one time just to show that we do get an answer that looks reasonable. But let's look at a couple more examples just so we can see exactly how this works in a situation where we don't have another way to easily differentiate. So I want to look at one problem together. If f of x equals x times e to the x, this is a good product where we don't already know what the derivative of x e to the x is, but we can differentiate x and e to the x. What I want us to do here is find the derivative, but also the second derivative and the nth derivative, excuse me. Not just the third or the fourth, but the nth derivative. So what's going to happen is we're going to see a pattern, and we're going to be able to use that pattern to figure out what the subsequent derivatives are. So let's start with the first derivative. Now, we've got a product, and so we've got our first factor is x, and our second factor is e to the x. And so we want to use the product rule, and it says that when we're taking the derivative of a product, it's the derivative of the first times the second. So the derivative of the first, well, the first factor is x, and the derivative of that is 1. Oops, didn't mean to do that in blue, but we'll just keep going. The derivative of the first times the second, that's e to the x, plus the derivative of the second times the first. Well, the derivative of e to the x is just e to the x times the first function is x. And we can factor out an e to the x here. And when we do that, we've got e to the x times, the leftovers are 1 plus x. But what I want to do just to make it look a little nicer, I'm going to actually put x plus 1 out front and e to the x there. These answers are equivalent, but I think this looks a little bit nicer, and you'll see why as we continue. So that's the first derivative. We then want to find the second derivative. So we need to differentiate what we just got. And you'll notice what we just got is, in fact, a product. The first factor is x plus 1. The second factor is e to the x. So again, we're going to use the product rule, which says we've got to take the derivative of the first times the second plus the derivative of the second times the first. So we start with the derivative of the first. The derivative of x plus 1 is just 1, because the derivative of x is 1 and the derivative of 1 is 0. So we've got 1 times that second factor, which is e to the x, plus the derivative of the second times the first. Well, the derivative of e to the x is just e to the x, and then times the first function is x plus 1. Again, we've got an e to the x that can be factored out, e to the x, and the leftovers are 1 plus x plus 1, and we know that when we combine like terms in the parentheses, that gives us x plus 2, because 1 plus 1 is 2, and then that's going to be times e to the x. So we've got x plus 2 times e to the x. We may or may not already be seeing our pattern. If you're not, let's do one more. Let's look at the third derivative of x. If you think you know the pattern, let's just do this one to make sure that it works. Again, we have a product of two functions. So the product rule says that when we're differentiating, we need the derivative of the first times the second plus the derivative of the second times the first. The derivative of that first factor, the derivative of x plus 2, is just 1 times the second function, which is e to the x, plus the derivative of the second function, the derivative of e to the x is e to the x, times the first function, which is x plus 2. We can factor out an e to the x, and that leaves us with 1 plus x plus 2 as the leftovers. And as probably many of you are already seeing, when we combine those like terms, 1 plus 2 is 3. So we've got x plus 3 times e to the x. That is the third derivative. And we can see a pattern emerging. If we want the nth derivative, well, notice each one has been in the form of x plus a number, and that number actually corresponds to the derivative that we're taking. And so we're going to have x plus the derivative we're taking is the nth derivative, and then times e to the x. So we have found a formula that tells us the nth derivative of the function x times e to the x.